Okay, in this video I will show you how to do the example problems from Unit 4, Lesson 1. Problem number 1 says a compact car, mass 725 kilograms, is moving at 100 kilometers per hour toward the east. Sketch the moving car with the velocity and momentum vectors. Okay, you should have a sketch that looks something like this, showing a car. And okay, you can't draw a car as good as me, just do your best. Showing the velocity vector pointing to the right, and also the momentum vector is pointing in the same direction as the velocity vector. So we're going to do part A now. We're going to try to find the magnitude of and direction of the momentum vector. So the mass, again, 725 kilograms. We want to find V1, which is in kilometers per hour. And remember, we need to have velocity in meters per second. So we're going to do a little unit conversion. We're going to convert kilometers per hour into meters per second. You remember your conversions. 1,000 meters is equal to 1 kilometer. And 1 hour is 3,600 seconds. So we're going to multiply by 1,000 and then divide by 3,600. That will cancel out kilometers, and it will cancel out hours, and we'll be left with meters per second. If you put it in your calculator, you should get 27.8 meters per second. Now we're ready to calculate the momentum. Remember, your formula for momentum is P, where P stands for momentum, equals M times V, or mass times velocity. So we're going to multiply the mass of the car, or 725 kilograms, times the velocity of the car, which we just calculated as 27.8 meters per second, and we will get our momentum in kilogram meters per second. If you put that in the calculator, 725 times 27.8, you should get approximately 20,100 as your answer, or 2.01 times 10 to the fourth, which is about 20,000 kilogram meters per second. So that's the answer to part A. Part B says a second car with a mass of 2,175 kilograms has the same momentum. What is its velocity? Let's sketch this situation. We have a bigger car. We have this big honking SUV with a mass of 2,175 kilograms. But it has the same momentum as the small car in part A. So let's draw the vectors here. The momentum vector, and we're going to call this momentum P2, which is the same as P1 above. What we want to figure out is, what is the velocity of car 2, or what is V2? So I'll put a question mark there for V2. Now, we're going to use the same formula we did for part A. Momentum equals mass times velocity. We want to solve it for velocity. So I'm going to circle the V. That's what we're solving for. So we're going to divide both sides by M, by the mass. Mass cancels out there. So you end up with V equals P over M, or velocity equals the momentum divided by mass. So we're going to plug in the same number we got in part A, 2.01 times 10 to the fourth. We plug that in for P because they have the same momentum. 2.01 times 10 to the fourth kilogram meters per second. Divide that by the mass of the car, 2,175 kilograms. Notice that kilograms cancel out and we're left with just meters per second for velocity, which is what we should get. So put this in your calculator. 2.01 times 10 to the fourth divided by 2,175. You should get about 9.27 meters per second as your answer. Moving on to the second example. The second example says the driver of the compact car, that's the first car, suddenly applies the brakes hard for 2.0 seconds. As a result, an average force of 5 times 10 to the third newtons is exerted on the car to slow it. Again, we're sketching the situation, and I should have done this before, but we need to add we should always add a coordinate system showing the positive is to the right or east and negative is to the left. So what we have here is we have a momentum that's positive, but the net force, which is from the brakes that I've drawn in as a green arrow, is negative. So we have a negative force and a positive momentum. That's why it's important to draw these vector diagrams to see what's happening and to see whether it's positive or negative. So to find the change of momentum, the formula for impulse or change of momentum is delta P equals net force times delta T. And for net force, we plug in negative 5,000 newtons. Again, it's negative because it is slowing the car down. It's going in the opposite direction of the momentum. We multiply that by 2 seconds, and we get a change in momentum for this car of negative 10,000 newtons, or in scientific notation, newton seconds. In scientific notation, that's negative 1 times 10 to the 4th newton seconds. And remember, newton seconds means kilogram meters per second. They're both the same thing, so it's a unit of momentum. Now, part B, complete the before and after diagrams and determine the new momentum of the car. Well, I'm going to show you a before diagram showing the car before the brakes were applied. Before we apply the brakes, the car has a greater momentum, which is the same momentum it had in problem number 1. So it has initial velocity, which was 27.8 meters per second, and it has an initial momentum of 20,100 from part A in number 1. After the brakes are applied, it's going to have less momentum. That applying the brakes is going to have a negative change in momentum, so after, we should show a smaller velocity and a smaller momentum on this car after the brakes are applied. So that's what I'm showing here. Smaller final velocity, and the momentum is going to be smaller as well. So there's our before and after diagrams. Now the problem asks us to find the new momentum of the car. So remember, at the beginning of the year we talked about if you have a change in something, like change in momentum, that means the same thing as the final momentum minus the initial momentum. So the change in anything is the final minus initial. So delta P is PF minus PI, or final minus initial. I want to solve for the final momentum. So what I'm going to do is I'm going to add PI, or initial momentum, to each side. So that will cancel out the initial momentum on the right side, and I'll be left with final momentum equals initial momentum plus the change in momentum. That is my formula for final momentum. Now I know what initial momentum was from problem number 1, is right here. It is 2.01 times 10 to the 4th. I'm going to underline that. See that? That was what the momentum was in part 1. We're going to plug that in for, oops, sorry, let me go back here a little bit. We're going to plug that in here for initial momentum, PI, and for change in momentum, we're going to plug in the number from above there, negative 10,000, or negative 1 times 10 to the 4th kilogram meters per second. So we have 20,000 basically minus 10,000, or to be more precise, 20,100 kilogram meters per second minus 10,000 kilogram meters per second. That leaves us with a final momentum after the brakes are applied of 10,100 kilogram meters per second, or 1.01 times 10 to the 4th in scientific notation. So basically the car has now half the momentum, approximately half the momentum that it had at the beginning by applying the brakes. Now, part C asks us to find the final velocity of the car. And this is a lot like problem number 1, part B. We're going to use the formula final velocity equals final momentum divided by mass. The momentum divided by mass will give us the velocity. So our final momentum we just calculated, 1.01 times 10 to the 4th kilogram meters per second, divided by the mass of the car. Now this is the smaller car, remember, so it's the smaller mass, or 725 kg. We divide those, cancels out the kilograms, and we're left with meters per second. And it comes out to about 14 or 13.9 meters per second is the final velocity of the car. Again, about half of the velocity that it had in part number 1, part A. Any questions?